Okay. Um, so the jump and kill flip-flop, and we talked about the characteristic table of that flip-flop. And because we have two inputs in J and K, we could have four possible combinations in which we could set up the JK flip-flop, and each of those input combinations relates to a particular state the flip-flop is in. So for example, if J and K are both 0, there is going to be no change in the outputs. Q and Q complement or Q and Q bar are going to remain as they are. So that's what we call the store state or the hold state or the memory state. And when K is 1, we are resetting or killing the output. So that's called the kill or reset state. And when J is 1, K is 0, we are setting the output or jumping the output. So that relates to the outputs being 1 and 0. And the last input combination is when J and K are both 1, which is called the toggle state. So whatever Q was earlier will flip. And all these changes in the output, Q and Q bar, can only occur just after the negative edge of the clock, because we are considering in this example a negative edge triggered JK flip-flop. So that's what we were talking about in the previous lecture. Now, to understand this a little bit better, we can actually go ahead and look at another table. This is also the characteristic table, and I don't have a column for clock in this case because I'm assuming that that is understood by everyone who is using the JK flip-flop, that the output can only change after the negative edge of the flip-flop, or it might change after the positive edge of a flip-flop if it is a positive edge triggered JK flip-flop. So when J and K are both 0, as you can see here, we are denoting the output. We don't have a column for Q next complement. I don't have that because that is just going to be the complementary of that column. So I don't have that for now. Okay. I'm just observing the Q next. So Q next means the output Q, the next suggests that it is just after the clock edge. And Q previous indicates the output Q just before the clock edge. So when J and K are both 0, Q next equals Q previous, which means that's a memory state behavior. When J and K are 0, 1 respectively, we are in the kill state or the reset state. Q next is independent of Q previous and it is 0. Similarly, for the set state, Q next is 1, independent of the previous Q, and it is set to 1. And in the last state, in the toggle state, whatever it was earlier, it might have been a 0, it might have been a 1, it just flips. So Q next is Q previous bar. So that's another view at the characteristic table. So as you can see over here, Q previous is also a variable that could hold two values. So we can in fact make this table into a slightly more detailed table. So what we can do is we can have a column for J, we can have a column for K, and we can actually have a column for Q previous or just before the clock edge. And then we can monitor Q next as the output that we are interested in. So if we did this, note to fill the table on the right, we are using the same information as is laid out in the table on the left, which is also the same as the table that we talked about earlier, which we call the characteristic table. These are all characteristic tables of JK flip-flop. Some are very concise, some are very detailed, but they're all variations of the JK flip-flop characteristic table. So let's see if we can fill out this table on the right. Well, now I have three binary variables that I'm considering as input. J and K are my actual inputs. Q previous is also behaving like an input because of feedback. So I'm treating this as an input in this case. And obviously, if I have three input columns, I'm going to have 0, 1, 0, 1, 0, 1, 0, 1, 8 options here that toggle at a particular rate. K is going to change at half the speed, two zeros, two ones, and so on. And then K is going to go four zeros and four ones, and so on. So I've filled up all the possibilities between three binary variables, 0, 0, 0, all the way to 1, 1, 1. Now, if I look at the Q next for J and K being 0, 0, as you can see here, J and K are 0, 0 here, they are 0, 1 here, they are 1, 0 over here, and they are 1, 1 over there. And for each of those, I am looking at both possibilities of Q previous. So if I look at the first two columns, when J and K are 0, 0, Q next is the same as Q previous. Well, Q previous in this case was 0 and 1, which means that my Q next has to be 0 and 1 respectively. So Q next equals Q previous when J and K are 0, 0. Similarly, for the next two, we are in the kill state, so it is independent of Q previous, and it is going to simply be 0. When J and K are 1 and 0, it is going to be independent of the previous output. It is going to be set to 1. And then the last possibility is of the toggle state. So Q previous, if it is 0, it will toggle to 1. And if Q previous is 1, it will toggle to 0. So that's going to be a little bit more detailed characteristic table. This actually will help us. The table that we drew on the right, I hope it is giving you a little bit more insight into that JK flip-flop. We can take this understanding to a little bit further. So what I'm going to do is I'm going to look at timing diagrams for a JK flip-flop. So when I say timing diagrams or timing waveforms, all I mean is I'm observing the inputs and the outputs with respect to time. So my x-axis, the horizontal axis, is time in this case. So to go through this, I will consider an arbitrary waveform for J, K, and clock. So let's say I have J to be 0, 1, go a little bit more, that. So I've arbitrarily sketched a J waveform going from 0 to 1 and 1 to 0 and so on. X-axis is time. Similarly, I will also try to sketch up something for K. So I'll start with, for example, 1. I will go to 0 here. Then I will go there. Another possibility for K. Now, just to make sure, between J and K, I have four possibilities. So my goal is going to be to see whether I am looking at those four possibilities or not. So over here, to begin with, K is 1, J is 0. In the middle over here, they are, K is 0, J is 1. For a little bit of time, they are both 0, and there a little bit of time, they are both 1. So I'm looking at all possibilities. So that's good. And then I can consider an arbitrary clock which goes from low to high at a particular speed. So let's see if I have um, arbitrarily sketched up a clock signal. Now, if I take a look at these three graphs, and just to make our, well, that's okay. So if we consider a negative edge triggered JK flip flop, so I'm going to draw the symbol that I'm looking at over here. I have edge triggering and I have a bubble in front, which means that I have negative edge triggering for the JK. So if that is the case, I will only have a change in the output when I have low, when the clock changes from high to low. So there and there and there. Those are the only times the output can change. Soon after those negative edges, the output can change. Other times, output is not allowed to change. Now, if I look at my Q, so the first negative edge that happens is over here. And at that time, they are both 0, J0, K0. So to simplify this, what I'll do is I will assume starting Q equals 0. So I'm assuming that my output at the beginning is 0. If it is 0, until we go to the first negative edge, it is going to remain 0. And the moment we reach that time, soon after that, so just with a little bit of delay, we are right now in the store state or the memory state. The reason being, when the clock goes from high to low, the negative edge, J and K are both 0, 0. So we are in memory. So if we are in memory for all this time, we are going to stay at 0. So we start at 0 and we store 0. We stay at 0 until the next negative edge. At the next negative edge, we have J and K to be both 1. So we are in the toggle state. So we'll toggle from a 0 to a 1. And we'll stay there until the next negative edge. At the next negative edge, we have K to be a 0, K to be a 1, J to be a 0, which means we will reset or kill to a 0. So that's how we can observe the output. So I hope this discussion uh, clarifies a few more things about the JK flip-flop, and everybody is sort of feeling a little bit more comfortable with at least what it should do. Okay. um, let's see if we have that. Let me actually